This video covers centripetal force. So in this section, we're going to look at objects moving in a circle or a semicircle, and they're moving at a constant speed. So these are the only situations that we'll be looking at when you're moving at a constant speed. Now, if you're moving in a circle at a constant speed, your velocity is always changing because direction is always changing. So changes in velocity mean acceleration. And in this case, the acceleration is towards the center. And we'll be calling it centripetal acceleration. So I know this is a lot of information, but it's very important that you write all of it down. In this section, we have an inwardly directed force which causes a body to turn perpendicular to velocity. What that means is if I'm moving in a circle, the whole reason that we're moving in a circle is because there is another force making us do a turn the entire time. So if these forces were not there, we'd want to move off in a straight line at any point, tangent to our circle. So one of the other things that's changing for this particular section is that forces that are directed toward the center are going to be positive, and forces pointing away from the center will be negative. Again, centripetal force always arises from other forces. Again, centripetal force is a summation of forces, and it is not a unique kind of force. So some of the forces will come from either tension or friction or gravity or normal force, some combination of other forces. It is not a force unique to itself. So for us, centripetal acceleration is going to equal velocity squared divided by r. Now again, because velocity is being squared, we're actually talking about our tangential speed. That's the speed that we're moving in that circle. And r will be the distance of the object to the center of the circle. Again, even if we're dealing with a semicircle, we're talking about this distance here. Okay? If it were a whole circle, what would be the distance to the middle? Basically a radius. A couple of other things that we can be asked to calculate in this section are period and frequency. Now, remember, we talked about period and frequency last year, but it came a little bit towards the end of the second semester. Period is the time it takes to complete one cycle. So if we're talking about uniform circular motion, meaning constant velocity in a circle, we want to know the time it takes to complete one circle. Also, frequency is the cycles per unit of time, and it has its own unit of hertz. So this is one relationship, T is equal to 1 over F. Another one that we saw last year was F is equal to 1 over T. Also, because we are talking about the speed as it moves along the circle, then we can say speed as it moves along the circle, then we can say that the circumference or the distance around a circle divided by the time it takes to go around the circle will give us constant velocity. So for this section, you're still going to be drawing free body diagrams, but remember that the centripetal force is not a unique force. It comes from other forces. So when you have a Earth going around the sun, then you can say, this is Earth, this is the sun, that the force that makes it constantly move in orbit is going to be your gravitational force. So in this case, your gravitational force would have been your centripetal force. For an object sitting on a rotating turntable, the centripetal force is friction. So for a rotating turntable, if an object does not slide off tangent to its motion or tangent to the circle, then friction must be holding it in. For a situation where you have a rock whirled horizontally on the end of a string, then tension is what's creating our centripetal force. So tension is our centripetal force here. friction was our centripetal force here. Now, in all these examples, I'm only showing one force that is your centripetal force, but it doesn't have to be that case. You can have, again, a sum of the forces that are your centripetal force. Like in this case, when you have an amusement park patron pressed against the inner wall of a rapidly rotating circular room, and we're talking about a gravitron, which we'll see an example of later. Okay. Here's where you have that person, and it's against this rotating room. The centripetal force here would be our normal force. Again, I talked about an example. Let's say that you are in a roller coaster cart and you are on the inside of the loop. Then there are two forces acting on you: normal force coming from the rails and gravitational force. Both of them pointed inwards towards that circle. So both of these together make up your centripetal force. Now the situation would be flipped. If I am on the outside of the loop, then gravity would be my only centripetal force, and normal would not be. But you would still write the sum of the forces as Fg, positive because it's going towards my circle, minus normal force would be equal to mass times centripetal acceleration. We'll do examples like this. Now remember, centripetal acceleration is the component of the acceleration, because remember, acceleration is a vector. It's a component of the acceleration vector in the centripetal direction. So, if an object is changing speed as it moves in a circle, then it also has a component of acceleration that is tangential to the circle. Again, in this case, the situations we'll see for right now, we're looking at a constant speed moving around a circle. But let's say we were not moving at a constant speed and we're actually speeding up. Then I would have a tangential acceleration as well as a centripetal. Before we look at some examples, I want to talk about two specific situations. These have to do with highway curves. Now, if you are turning on a flat surface, the force that makes you turn is going to be friction. You have static friction that's pulling you towards the center and helping you make that turn. Now, if you are on a curved surface, or a banked curve is what they're called, then the normal force, or a component of the normal force, is what's going to help you, again, make that turn. So in this case, especially with the banked surfaces, you are not going to be separating mg into components, because our acceleration won't be in the direction of mg. It'll actually be in the direction of our normal force components. So this piece right here, this n sine theta, is what's going to be our centripetal force in this case. So in this example, we're asked to find the minimum safe turning radius for a car traveling at 26.8 meters per second, or about 60 miles per hour, on a flat roadway, assuming a coefficient of static friction of 0.7. So again, here we always want to start with a free body diagram. So we have our normal force acting up, we have our force of gravity acting down, and then again we have our frictional force acting inwards. Now again, remember that our static friction will be equal to mu times mg, or mu times our normal force, which in this case is mg. And we want to set this equal to our centripetal force. So this is mv squared over r. Here we notice my m's cancel out. And I'm trying to solve for my r, so I get r by itself is equal to v squared divided by mu times g. When you put in all of your values, you should get an r value of 104.7. meters. In this example, we have a 200-gram mass is attached to one end of a string of length 80 centimeters. The other end of the string is tied to a fixed point on the ceiling. The apparatus is set into motion so that the mass moves at a constant speed in a circular path, and the string traces out a cone with an angle of 30 degrees. Now we're asked to determine the tension in the string and determine the tangential speed of the mass. Again, we're solving for our velocity. So here, we do want to start with a free body diagram. I know that the force of gravity is acting downward. I have a tension acting upwards. And we have our angle that is created with the vertical here. So this piece will be t cosine theta, t sine theta, and mg. Again, writing the sum of the forces in both directions, I have t cosine theta minus mg is equal to 0. Again, it is not accelerating in that direction. So we know that t cosine theta is equal to mg. And t sine theta is going to be positive because it's going towards the inside of my circle. So that would be true at any point in this path. Again, t sine theta are the sum of my forces in the centripetal direction. So it's equal to mv squared over r. So before we continue, what we're asked to solve for is my tension. So if I know mg and cosine theta, then tension will be equal to mg divided by cosine theta, which gives me a value of 2.3 newtons using gravity as 10 meters per second squared. So we solve for our tension. Now that we know our tension, we can go back to this equation and solve for my velocity. So it's a good idea to solve in terms of variables first. So we have r times t sine theta divided by my mass, and then we take the square root of both sides. So my velocity will be, so one problem that we're going to run into, I just remembered, is that r is not given to us, but we can calculate r. So our length of our string is 80 centimeters or 0.8 meters. So that's this piece right here. And r is going to be this distance. So what we notice is that it creates a right triangle at all points. So r will actually be equal to L sine of theta. So I can replace r with L sine theta times t sine theta, all divided by my mass. And you should get a value of 1.5 meters per second. Again, this v is not really a velocity. This is our tangential speed. In this example, the masses are attached to each other by a string that passes through a tube. Mass m1 is equal to 0.6 kilograms, is spun in a circle of radius r is equal to 60 centimeters, at a speed sufficient to keep the mass m2 equal to 1 kilogram stationary. We are asked to solve for the centripetal force and to determine the tangential velocity. So again, free body diagrams. We have tension going up, m2g going down. Here we have tension at an angle, and m1g going down. So we can see that this tension can be broken down into two components. Now I'm not given an angle, so I'm not going to add cosine and sine just yet. But I know that this will be my tension in the x direction, and this will be my tension in the y direction. So again, if the second mass over here, m2, is stationary, that means that T is equal to m2g. So if I'm asked to solve for the centripetal force, in this case Tx, then that's going to be equal to the square root of T squared minus Ty squared. Again, this comes from Pythagorean theorem. So T will be m2g squared, and Ty squared is going to be m1g squared. So again, it is not accelerating in this direction. It was only accelerating towards the center. So Ty was equal to m1g, and T was equal to m2g. So my centripetal force, when you put in all of your values, here I'm going to go ahead and use 9.8. I get a centripetal force of 7.84 newtons. Now I can solve for my tangential velocity. Again, if I know my centripetal force is going to be equal to mv squared over r, then I can say that r times tx, for now, divided by m is equal to v, and then square rooted. Here our r is given to us, it is 60 centimeters or 0.6 meters. So with all of my values, I should get a velocity of, or tangential speed of 2.8 meters per second.